Um, First of all, thank you everyone for coming to the session this morning. I can imagine it's hard after the replay party last night. I hope several of you made it to the party last night. That's good. So my name is Nihar Bihani. I'm a product manager at Amazon Web Services. And I've got a couple of colleagues here with me also. I'll introduce them in a little bit. But we'll talk today about Cache is King. That's the title of the talk, Scaling Your Application While Improving Performance and Lowering Your Costs. So let's get right into it. So now, we've all heard this expression that cache is king. And sort of the session of our title is also a play on this as expression. But that's not the cache we'll be talking about a whole lot in this session today. We'll be talking about CACHE, Cache is King, which is a component that you can use to store a local copy of your application close to your user, so you can deliver that object or that content to your faster to your users. But if you think about it, the two terms, cache and cache, spelled differently, are really quite similar. And here's some data that shows that cache is cache. And what I mean here is, a study, and if you look at this study, this says that a 1-second delay in the page load time for a website can cause 7% loss in conversions. So if you have an e-commerce website that does $100,000 in revenue on a given day, then a 1-second delay in the page load time for that website can cause you to lose $2.5 million in sales over the course of a year. So that's just fewer page views, less customers are satisfied. But what we hope to do in this session is give you some tips and ideas on how you can take caching of your resources and use that to your advantage to improve that page load time, to improve your customer's experience, and hopefully helps you earn more cash at the end. So let's look at a little bit more data to see how caching might be a problem today, or maybe how you can use caching to your advantage. So I'm not sure if you're familiar with Httparchive, but this is a website that's run by Steve Souders. Steve Souders is pretty well known in the web performance arena, and he runs this website where he's measuring the performance data for the top 1 million websites based on Alexa rankings. And he's looking at things such as the size of objects on your website, cacheable resources, error rates, and so on. And I wanted to look at this one specific chart from his website that shows how many of your objects are actually cacheable or static on your site. So on a typical website, looking at the top 1 million sites, you can see that a very high percentage of objects on this site are actually cacheable. They can be cached. But the other data that's really startling is that only 44% of these resources are actually being cached. So there is a 56% of cacheable resources, which I think of as lost opportunity. These are resources on your site, whether that's static images or other resources that are reusable, that could be delivered, they don't change frequently, could be delivered to multiple users, and you could take advantage of caching, but a lot of the sites today are not doing this. So the goal for the rest of this talk, myself and my colleagues, is for us to help you cache everything possible. So what does that really mean? Well, the way we've decided to sort of structure the talk is by looking at the different layers of your application. You can start with the browser. That's the device that your users are using to interact with your application, to view your application. Next, we look at proxy servers, or servers at the edge of the internet really close to your users, and what could be cached at those edge locations. We also look at the web tier, so the web servers that are actually serving your application's traffic and fronting your application that sits in the data center. Then we also look at the web tier, the application tier, and the database tier, and see how caching could be implemented at each of those layers of your application stack. So I think of this in terms of layers. So we decided to use a layered cake to think in terms of how different layers of your application and how you can cache at each of these layers. So we have the browser, the edge, web cache, application, and database. I'll talk about the browser cache and the edge cache. And then my colleague here, Chris Muntz, he will come up and he'll talk about the web application and database cache. And then what I'm really excited to introduce, is we have a customer representative with us here today, Stephen Evans, and he's from the Toronto Star, which is the largest newspaper in Canada. And once Chris and I have gone through how you can take advantage of caching and some of the techniques at each layer of your application stack, Stephen will talk about how, for all the applications that him and his team are responsible for at Toronto Star, how they take advantage of caching at each of these layers of their infrastructure stack. All right, so let's dive right in. So as we dive into the details, one of the questions that I just want to ask is, why are page loads so slow? Why don't pages load faster when you go to an application? And I think the answer there is, at least in my mind, because the internet is slow. Because the speed of light is slow. The speed of light is only 300,000 kilometers per second. And when you send data over glass, over fiber, that's even slower. It's only 200,000 kilometers per second. So that's the fastest that your packets, your data can travel over the internet. So let's put that into perspective. Let's look at a real-world example. So I look at the download performance. So I did a ping from my home in Seattle to a server that's sitting out in New York. And the round-trip time for this ping was just over 13,000 kilometers. So going from Seattle and then going to New York and then coming back. So based on 200,000 kilometers per second, this would come up to theoretically 65 milliseconds as the round trip. And then when I do the actual ping, I measure 68 milliseconds as the actual round trip time that it took for that ping. So the theoretical and the measured round trip times pencil out. So that's good news. But what does this mean in terms of downloading an object? This is just one round trip to that server and back to the client. So let's look at it in terms of downloading an actual file and what's involved there and how many round trips may need to happen there. So at the very beginning, the client makes a connection to the server, and there's a TCP connection that's established first. So there's a SYN that's sent to the server, and then the server responds back with a SYN ACK. So that's one round trip. So that takes 68 milliseconds in this example. And then once that connection is established, the client responds back confirming that the connection is established with an ACK and asks for the image to be downloaded. And then the server sends this image back, so that's the second round trip, another 68 milliseconds. So now we have 136 milliseconds for the first few bytes of this object to start arriving on the client, on the browser. Depending on the size of the object, there may need to be other round trips involved to get the rest of the object down on the browser. So our goal should be to minimize this round trip time, this total time rather, the 136 milliseconds, as much as possible. So let's see how we can do that via the various layers of our application stack. So starting with browser cache, this is probably the fastest that you can deliver your object to your users, because your object is cached on the hard disk of the device that they're using. The browser can just get it in, not milliseconds, we're talking microseconds here. So the request does not need to go on the network at all. You're completely avoiding the request going on the network. And you do this simply by setting the max age header or the expires header on your objects, and most modern browsers will honor these headers and cache the object when possible. For HTML5 applications, the browsers that support HTML5, you can also use the manifest file, which is simply a text file where you specify which of your pages should be cached for offline access. So that's another mechanism that you can use. You simply include the manifest attribute in the HTML tag of your document that you want to be cached. So as I said, this helps completely eliminate network latency, which sounds great on the surface, but what's the catch? The catch is browser cache size is very limited. And you, as application developers, have no control over changing that size of that cache. So in addition, you're actually competing with all of the other applications that your users are viewing on that same browser. And it's the same shared cache size that all of these applications are sharing, including yours. So the chances of your application, your pages getting cached there, probably really low. So let's talk about edge caching and how you can use that to your advantage. If your request does need to go out on the internet, how can you minimize the time for that client to get that data back from the server? So going back to our original example, this server is sitting all the way in New York City. What if we had a server that was sitting much closer to the client, much closer to that location in Seattle? Now you can do the 2 round trips that it needs to take, but the server is only 10 milliseconds away. So you're caching at an edge node, and in this example, it's an Amazon CloudFront edge node. CloudFront is AWS's content delivery network. So a server in CloudFront could be caching this piece of content, and the client can get this in 20 milliseconds now. So the 20 versus 136, big difference there in terms of the time it takes for your client to download this object. Now, again, this object does need to be at the CloudFront edge node. It needs to be cached there. If it's not, then CloudFront would have to go back to the original origin server in New York and download that content from there. But using a CDN like CloudFront can still help because CloudFront maintains a persistent connection back to your origin server. So CloudFront is not doing 2 round trips back to the origin. It's really only doing 1 round trip because it asks the origin directly without needing to establish that initial TCP connection, because that's already present, and just asks for the image and starts downloading the first few bytes of that image in that single round trip. So even if the object is not cached at CloudFront, we're talking about a 68 millisecond round trip from CloudFront to the origin over the long haul, and then another 20 milliseconds from client to CloudFront. So it's 88 milliseconds, which is still much lower than the 136 milliseconds. So as I said, CloudFront is a global content delivery network. There are 46 edge locations that CloudFront has around the world. And chances are that where your viewers are in the world, there's an edge location really close to them versus going all the way to a single origin server that you may be running, for instance, on the East Coast. So the way CloudFront works, the viewers connect to a CloudFront edge location. The edge location can respond back with the object if it has it in its cache. Otherwise, the edge location will go back to an origin server, which could be an Amazon S3 bucket, an Amazon Elastic Load Balancer, or maybe even a custom origin server that's running in your own data centers. So when it comes to edge caching, how do you decide what to cache at the edge of the internet on a content delivery network? So the way I like to think about it is, let's look at the different types of content that you have on your site and see if each of those content types can potentially be cached at the edge by setting the right cache control headers and utilizing a content delivery network. So we have static or reusable content. These are the images and so forth. You can have customized content. You can have some media content on your site, and also potentially dynamic or unique personalized content. So let's look at each one in some detail. So first, static content. This is the chart we saw earlier in the presentation, where 56% of static resources aren't even being cached today on a typical website. So, images, CSS, JavaScript, taking advantage of a content delivery network and setting a long max age or a time to live on that particular resource or object will allow that edge server on the CDN network to cache this object for a long period of time and serve that locally to your viewers who are requesting that. And I wanted to give a customer example here. This is the picture of the Curiosity lander that the event was hosted by, or delivered, the website experience was delivered by Amazon Web Services. So NASA JPL, Jet Propulsion Laboratory, used AWS, including CloudFront, to deliver the website experience and the images to their viewers. And when the images arrived from the Curiosity rover down to Earth, it almost sounds crazy to say that, JPL cached these images for a long period of time on CloudFront so that all the viewers who were requesting this image could get it from a cache server very close to them. Let's talk a little bit about customizing or customized content. So in addition to static content, customized content on your site could also be cached, maybe for a shorter period of time, maybe not for an entire day, but a few minutes or a few seconds at a time even. That can help scaling the delivery of this type of content to your viewers without those requests necessarily going back to the origin server. You would typically customize content on your site by using either cookies or query string parameters, and CloudFront can be configured to forward both cookies and query strings back to the origin server, and then those values can be used at the edge servers to customize the cache version of your page. So this is another way you can cache even more of your content on your site, something that you may not intuitively think about caching, but could be cached at an edge server close to the end users. I wanted to give another example here. Earth Networks, who's a CloudFront customer, they use cookies to customize the weather data on their application. And even though the URL is the same, the zip code cookie value could be different, and so the data on the page is different. And they cache this page with the cookie value for a short period of time, say 5 minutes, at the edge node, so that everyone else in that geographic area who wants to look at the weather in Las Vegas can go to this page and get a cached copy, even though this is customized to the Las Vegas area, and almost an example of personalized dynamic content, really. What about video content? So video content can be, it could be especially helpful to cache video content at an edge server close to your viewers, because video content generally is much larger in size than static objects or static images on your site. In addition to that, with video, there is a large fragmented ecosystem today of different devices, different protocols that you need to deliver your video content to. And a content delivery network can really help simplify that fragmentation and help you deliver to all of these different devices and in those different protocols in a much simpler way than you needing to worry about that in your origin servers. So I'll give you another customer example here, PBS, who's been a long-time AWS and CloudFront customer. They were using another CDN previously, but they moved over to CloudFront because they saw better performance and got lower costs from using CloudFront. And today, they deliver a vast majority of their streaming video content over the CloudFront Edge network. So a lot of that content that you may be seeing on their website is cached at a CloudFront Edge server close to you. What about a live stream? This is something where you might think, well, the stream is being generated live. How can you take advantage of caching for a live event? So if you're doing any live events, you can still take advantage of CloudFront by CloudFront fronting the media servers that could be an Adobe Media Server, Windows IS server, or a Wowza Media Server running on EC2. And CloudFront can still be caching the live stream generated from that media server and help scale the delivery of that live stream to all of your viewers around the world. So I'll give you another customer example here. A very recent one, just earlier this week, we used Amazon CloudFront to live stream both the keynotes on Wednesday morning and Thursday morning from right here in Las Vegas. So we had a crew here capturing the live event, encoding it on site, and then sending it to a media server in Amazon EC2. And then CloudFront was sitting up in front of those media servers, taking the live stream, caching it, and delivering it out to all of the viewers. So we were able to scale to thousands of viewers for both of the events, and CloudFront handled 90% of the traffic from its edge servers from cached stream, and had to go back to the media server in EC2 only 10% of the time. So that's a great way to not have to scale your origin media server instances, and let CloudFront handle the scale and reduce your cost at the origin. And then finally, what about your dynamic content? You could also have some dynamic content on your site, and this content typically has 0 TTL, so can't really be cached. Should you still take advantage of CloudFront and put CloudFront in front of your dynamic content on your site? So I'll go through this quickly. We had a full hour session earlier in the week, and I'd encourage you, if you missed that, to see the video recording of that after the event, where we went into great depth about how CloudFront can help accelerate the delivery of dynamic content when dynamic content is proxied via CloudFront Edge location. So I won't get into too much details here, but CloudFront has TCP/IP optimizations, keep alive connections that really help speed up the delivery of this content, even though each request could be considered a cache miss, where CloudFront won't have that object in cache and needs to go back to the origin server. You can also take advantage of CloudFront for SSL termination and for post-put upload optimization and offload your origin servers, just like the way we did with the live stream example, and let the edge servers handle a lot of that scaling and a lot of the load. And finally, CloudFront for dynamic content, the pricing for CloudFront is the same as static content delivery, so it's really low, same as other AWS services, pay-as-you-go pricing model. So I'll give you another customer example here. We recently launched support for post-put upload optimizations. So CloudFront was primarily a download-only CDN that supported only get and head, but now you can also do post and put as well as other HTTP verbs. And Uyala is taking advantage of this feature to accelerate their RESTful APIs and has CloudFront in front of their API endpoints. That helps them minimize packet loss and upload latency for their API users. So at this point, I'll hand it over to Chris to walk you through some of the other layers of your infrastructure and how you can take advantage of caching there.
Thanks, Nihar. So my name is Chris Munns. I'm a solutions architect with Amazon Web Services based in our New York City office. And I work with customers of all shapes and sizes and helping them build on AWS and scaling their websites. So we're going to dive into the rest of our layers of our cake here today and talk about some of the other things you can do to cache content and cache all sorts of data in your applications inside of your infrastructure. So Nihar talked to us about browser caching and edge caching, stuff that would typically sit outside the 4 virtual walls of your infrastructure as it may be. So we're going to dive in a little bit deeper. So first up, though, as my mother would tell me, you can't have your dessert until you have your dinner. So before we can get into our layer cake here, I wanted to talk about an experiment that I did in preparation for this presentation. So Nihar talked about how Httparchive has this wonderful amount of information about public website requests, how many HTTP requests per page, the type of objects that they are, how well they are cached or not cached. He gave the statistic about how 56% of cacheable objects aren't cached properly. But it's actually really difficult to find out information comparatively for inside of an infrastructure. There aren't too many people who have published studies or published even blog posts about, hey, we added caching to this layer, and this was the result of it. So we like to do things as data-driven as possible here, so I decided to come up with a really brief, small experiment. So I did this experiment as I took a single EC2 instance, a single non-multi-AZ RDS instance, and then I ran the Drupal Commerce Kickstart application on that EC2 instance. So Drupal Commerce Kickstart is just a distribution of Drupal, has a lot of e-commerce functionality in it. It was running in Linux, just running latest Apache, latest PHP that I had in Amazon Linux, and I also had an elastic IP address on the EC2 instance. So once I had that environment up and running, I then proceeded to use a load testing tool to throw about 8 million requests at it, 40 per second from 4 other nodes in a different EC2 region. Not a huge amount of traffic, really, but going at a single instance, it's actually quite a lot of traffic for that one instance to handle. And then because I need to gather some data, I made use of New Relic's PHP agent, as well as the webpage test.org website to do some profiling of what the results are of my tests. So again, this is the infrastructure. I had my clients, my test nodes talking to an EIP, attached to an EC2 instance. The EC2 instance talked to RDS for the database that Drupal needed to talk to. So the results really weren't that great, actually. Again, this was just the basic default setup. There was no tuning put in place. Fired up an instance, installed it, ran the basic configuration. What I found is that very easily the requests that we're throwing at the host completely maxed out CPU, maybe used about 75% or so of the available memory on the instance at any given point in time. But what New Relic was able to tell me is that what I was looking at was almost 15-second page response times at the server. So this isn't in the client, this isn't in the browser, this is the server serving up the request for this home page for this Drupal Commerce Kickstart application. It resulted in a really low requests per minute. Here, about 159 requests per minute. That works out to maybe 2 or 3 requests per second. And since I was throwing 40 requests per second at it from these different hosts, you can see that everything was very well backlogged going into it. And then lastly, from webpage.org website, I could see that I was serving up mostly static content. Almost 95% of the requests to the server were to serve up just static assets. So again, basic setup, nothing tuned here. Didn't expect anything really fantastic. Was really surprised by actually how poor this kind of performed. So we'll get back to the experiment a little bit later after we talk about some of the caching techniques here, and we'll see how we're able to change things up. So again, going back into our wonderful layer cake of caching today, the first stop is going to be talking about a web cache. So web cache is going to be a caching layer that typically is sitting between your web or application servers and either your users or your CDN, with the idea that you're going to be caching usually static HTTP resources before serving them out to, again, your users or to that CDN. So it's going to reduce the load back onto your web or application tier. It's also going to improve performance going out to your CDN network. So there's a general really good win all around. There's a number of different popular solutions. One of the most popular ones today that I continue to run into customers using is Varnish, really great piece of open source software. Up next are web servers hopefully you're all familiar with, Nginx, Apache. They both have modules and ways that you can configure them to do some better caching. Next up is Squid, a tool that's been around for a long time, but still very performant, very popular. Another tool called Purball. Don't run into it too often, but every now and then I do see people using it. And then lastly, there are language-specific frameworks. So this was a PHP application. There are caching tools like APC and Zend and several others that I can make use of. And again, depending on the language of your application, there might be other different third-party pieces of software that can do some post-page generation caching before it's served out. So if we were to look at an infrastructure here, excuse me, that we would be applying a web cache to, pretty straightforward infrastructure. My caching layer lives here in between a forward-facing elastic load balancer that acts as origin to my CloudFront CDN, and then pushes back to an ELB that would talk to my web tier. And if we were to think about how a request would come into the stack and back out again, customer would generate the request, go to CloudFront. CloudFront could potentially be passing it back to my ELB, which would pass it back to my caching tier. And if the cache hadn't been warmed or there was nothing in there, it's going to pass it back to its origin, or its source for data. So back to my ELB, back to my web EC2 instances, and then the request will return back out again. So again, back to the ELB. But now this time when it hits my cache instance would be caching that data for further use. And then the request would get passed back out to our customer. The next time that our customer makes this request, it goes back again through CloudFront, back to our ELB, and then onto our cache instances. This time, though, because we have the data in our cache is going to serve this up. So you can picture how this could be really valuable for your content on your website that maybe isn't changing too often. It's not very highly dynamic. We're reducing a significant amount of load off of our actual web layer. Oh, sorry. So the request then we go back out from our cache tier. So some general guidance for a web cache. The advice that I always recommend is opt for something that is acting out of memory as opposed to something from disk. You want your cache to be fast. You want it to be quick. You don't necessarily care about the persistency of this cache, so you can feel comfortable to use a tool or an application that's going to serve this data directly out of memory. It's It's going to be much, much faster and much more performant. You really want to pay attention to the metrics that come out of whatever caching tool that you use. You want to pay attention to the hit ratio, the miss ratio, how often you're evicting objects from your cache. I have seen customers that have caches that are way too small for their content. And so there's a very high eviction, and so they're actually not getting the best use out of it. So you want to pay attention to those ratios. They could guide you towards either increasing the size of your instances or increasing the pool of instances that you have available. You also want to pay attention to whatever sort of TTL you might be setting for your cache. The inverse of this is of having too many evictions or too many misses is that you could potentially be caching data for too long, which means that on a new code deploy or on some sort of other change to your application or your website, your customers may not be seeing the most recent data. And then lastly, you want to pay attention to what ways you have that you allow the cache to be broken. So typically, sometimes, depending on if you have certain cookies set, you may not want the request that a user made be cached on the website. I read a story about a company that was not doing this properly and was doing some web caching where they were caching dynamic pages for their users. Because they were not paying attention to session IDs and cookies, every now and then, every user on the site would seem as if they were logged in as the same person. So you could have user Sally and user Bob and user John, and basically based on whoever's dynamic page was cached first, they all looked like they were the same person. So it's another thing you need to be cautious of and be thinking about when you're designing to use a web cache. Also, how do you go about deciding what it is that you want to cache? My general recommendation for this, again, paying attention to the kind of cookies that you allow to burst the cache, is to do things like cache every page for a user that doesn't have maybe a session existing. So if they haven't logged into your website, right, if they haven't logged in to maybe add something to a cart or go through some sort of other action, you should try to cache as many of the pages that they're going to be interfacing with versus when they're logged in. Next is obviously anything that is a static page. So let's say that your website has things like help guides or informational pages or a knowledge base or product pages, things that really don't change too often. These are things that you can very easily cache and set a long-lived TTL for without having to worry about storing content that you shouldn't or serving content you shouldn't. Next is doing some basic analysis with traffic logs. So whether they come from your web servers or your CDN, taking a look at all the requests that are being made, all of the data that you're serving back out, and figuring out what ratio of that is non-dynamic content. Most people are surprised when they find out just how much static content they are serving out in terms of HTML. And then lastly, even really small TTLs. I've seen TTLs as short as 20, 30 seconds being drastic improvements to the load being reduced from a back-end infrastructure. TTLs as low as 60 seconds can be incredibly valuable if you take an application that's getting a couple thousand requests per second. So moving down to the next layer of our wonderful caching cake today, we're going to talk about application cache. So coming in one level underneath our web cache here, application cache is going to be something that, from an application level, you're going to be caching resources. Things such as session information, temporary application information, metadata, cart information, intermediary process information, things that maybe don't belong directly in a database, but that might have been pushed forward to you by a user for some length of time inside of a session. So popular solutions for these, some really common ones here, Memcached, Redis, Cassandra, and then Amazon DynamoDB. So looking again at our infrastructure here, we've seen that I have added in now Elasticache into a different subnet in my VPC, or subnets I should say, and our web and app instances would now be talking to this tier for this data. So our application requests would come in again from our CDN to our forward-facing load balancer and get passed back. I had mentioned before DynamoDB as a solution for this, and anytime that I bring this up with people who aren't aware of this, they're usually a little surprised. So we actually have in our PHP SDK a PHP session handler that is backed by DynamoDB. It uses all of the same native calls that you would find in the PHP session handling framework, but it backs it by DynamoDB. So what it can do is it can give you an incredibly low latency, yet highly persistent session store. So instead of having it stored in memory, having to worry about potentially losing it, or storing it somewhere on disk and not having it be as performant, you can actually get the best of both worlds by storing the session data in DynamoDB. And you can grab this code from our SDK again, and there's some examples in the documentation of how it works. And so how that would look in our infrastructure here, because DynamoDB is an internet-facing service, is that we'd have to provide some method for us to get from inside our VPC out to DynamoDB. And I'm doing this, all of my, my network diagrams in VPC. Hopefully, if you've been going to some of the great sessions this week about VPC and building in VPC, you know that it is definitely the thing to be doing. So in this case, I've got some Squid proxy servers. They're actually passing requests from my web and application tier out to DynamoDB. So typically, people might think that they would do this via a NAT instance, and that is another common way to do it. But you can actually set up Squid proxies as a reverse proxy from inside your infrastructure to outside internet services. We have a really great tutorial and article on our website for this. Talks a little bit further about how it would work and how this can give you a really high-scale solution for doing out of your VPC to internet service calls. Use cases, again, for application cache, session information, temporary data from your application, and then really interesting things like rate limiting. If any of you have a publicly facing API or, say, publicly facing ways that your users can interact with each other, maybe member-to-member emails, chats, ways that they can do things on your system, it's actually really important to implement some sort of rate limiting. And so what I'll see people do is keep that rate limiting information in an application cache such that it's very lightweight and you can very easily access it. And then lastly is things like counters. So views, scores, leaderboards, stuff like that. For those of you that are Twitter users, Twitter actually serves out your Twitter feed via Redis, essentially acting as an application cache for you. So how do you decide where to cache here, or what to cache? Ideally, you treat the data in this cache as being tolerant of loss. So again, this caching layer is not a place where you are storing any persistent data. Typically, you're storing data either that your user already has, would be providing to you via cookie, or that maybe is something that is generated through the application and could be very easily generated again. So you're typically not looking for persistence at this layer, though you certainly could be. And you're also looking for things that typically don't make sense to store in a database because it could be potentially too hot for a database, too much load, too much traffic, and it may not make sense in any sort of structured database. And then lastly, you want to look at any sort of data that your application might be generating, even intermediary inside of a process, inside of a page load that it might need to generate a request again. Instead of constantly having that load in your application, take that data, push it out to a cache, and be able to call it from there. So moving down into the bottom layer of our cake today is database caches. So again, pretty straightforward. The idea here is that we would be caching database queries in some sort of other tier. This could be a separate tier. It could be a tier on the database. Pretty much all major databases today have some form of query cache that would live in the database engine. And this could be any sort of query you have that would be repetitive and that you don't want to have continually running against the database. Popular solutions for this, again, pretty much every major database out there today has a query cache that you can easily enable. Beyond that, Memcached continues to still be a very popular solution for this. And that could be on dedicated hosts, where I'll talk about in a minute about how MySQL 5.6 actually offers up Memcached local to the database, which is really something kind of interesting. And then also I see Redis being used here pretty heavily these days. It's becoming a very good option for doing this. Word of caution here. I'm actually not a huge fan of in-engine database caches. There are a lot of people, a lot of results that you'll see that you can cause a large invariable impact in performance to your database by having memory used for a query cache. So for things like MySQL, you would have to worry about what space you were using up for the query cache that couldn't be used from your normal buffer pool and how that could affect other query performance. So where would this live in our infrastructure? We had already mentioned where Elasticache would live, so we could potentially use that again in this tier. And then you could be talking again to an in-database query cache on your database infrastructure. In this case, I've got RDS, maybe running MySQL or Oracle or SQL Server or now Postgres using the local query cache. In terms of how this works, I just wanted to give a really quick sample. This is basically some very basic pseudocode for using Memcached to cache a database query. Very, very basic sample, maybe not the best way to do it, but essentially we have a function where we are trying to retrieve from our cache some information based on a query. So we pass in the query. The first thing that we're going to do is actually create an MD5 sum of the query. We would use that as the lookup key in our cache. We then go and query our cache for that lookup key. If we get back the result, we return it back to our application. If we don't, we would query our database, take the result, put it into our cache, and also serve the query response back out to our user. So again, very simple, couple of lines of code here. This is something you could drop into an application, and any place that you make a query, instead of calling your query handler directly, call this function, which could then pass it back to the others. So I had mentioned really briefly before that MySQL 5.6 now has support for built-in Memcached. This is actually something really exciting because the two have been paired up traditionally for probably going on about 10 years now. And so what they've done with 5.6 is you can actually run Memcached inside of MySQL, where the in-memory space is actually backed up by DynamoDB, the DynamoDB engine on the host. So you get the best of both worlds from having a really high-performant key value store in memory, and then you have this really strong persistency that you get from DynamoDB. So a really cool thing that is definitely worth exploring. And I talked a little bit before about how do you make decisions about what to cache, about what to change in your application to make sure that content is cached. We've got a lot of really great partners in this space. So I mentioned how I was using New Relic to get information for the mini kind of experiment that I did. There's a number of really great companies that you can go see on the exhibit floor this week if you haven't had a chance. Companies like Boundary and Sumo Logic and Loggly and Datadog. They all provide a number of different services that can help you do really deep profiling of your applications. It's really difficult to do things like caching at all layers unless you're doing really good profiling of your application and of your infrastructure. So let's go back to our experiment here. So initially, this is what our infrastructure looked like. Customers talk to, or clients talk to an elastic IP, attached to an EC2 instance, talk to a database. We didn't have really great performance, right? Almost 15-second response times. Mostly static data, really low requests per minute. What I did was I added in an Elasticache node running Memcached as another instance. I put CloudFront in front of my website. So instead of hitting that EIP directly, I was now going to hit a CloudFront distribution. And I also lightly tuned my Apache server such that it would add expires and good cache headers to my static content. So all the CSS and JPEGs and PNGs and JavaScript I was serving up. I also added into Apache APC, which is a PHP cache that will cache the compiled PHP code in my application. And all I did was increase the default memory limit that it uses from 64 megabits to 128. I did absolutely nothing to the database, no query performance tuning, no new indexes, no on-database query caches. I didn't need to do any of that. And then all I did for my code was I added in the public Memcached and CDN Drupal plugins and configured them to point at the different services I was setting up. So this is what my new infrastructure looks like. My users are talking both to CloudFront and then back to my origin for my web page, for my application, sorry. My web and app instance then is talking back to both Elasticache and to RDS to get the database information that it's looking for. So what were the results? So response time went down by half to roughly 7 seconds. Still not really fantastic, but again, I was throwing 8 million requests at it, 40 per second from 4 different hosts to a single host. So this was still a pretty drastic improvement in performance. While I was able to drop the response time by half, I was able to almost double the requests per minute. So having both of those change actually skews it quite a bit in terms of the increase in performance that I'm getting. And then with CloudFront in front of my application, I had talked before about how roughly 9 and 10, or even more than that, almost 90% of my requests were for static assets. CloudFront was able to bear the brunt of that, taking a repeat page view time, load time, from 15.8 seconds down to 2.75 seconds. So a very drastic change without me having to do a whole lot of work. And as I like to say, going along with our food theme today, it was easy as pie. So hopefully you've got to learn a little bit more here about some of the other layers of caching that you can do. I'm going to hand it over to Stephen now from the Toronto Star to talk about how they use caching at every layer.
Just doing a technology check here. Hi, everyone. I'm Steve Evans. I'm the head of digital technology at the Toronto Star. I'd really like to thank Amazon for inviting me down here to Vegas on this warmish autumn day. I think it's about 55 degrees in Toronto today, so we're doing a little better here. So my goal here today is to give you a fairly quick overview of what we're doing at the Toronto Star in terms of our technology stack, and specifically the different ways in which we're using caching at the various tiers that Chris and Nihar have already talked about. So quickly, an overview of what is the Toronto Star. We're Canada's largest daily newspaper. Our focus is on the Metro Toronto area, but we also cover national and regional stories. We have about 3.3 million unique visitors a month, so it's a fairly large site. Interestingly, we kind of rebooted our process about 2 years ago. We decided to build a new technology function really as a startup within the organization. So I was hired to build out that team, and part of that process was to redesign our infrastructure, rethink how we're hosting and using cloud-based hosting. We have a pretty diverse tech stack, run the gamut from Java, PHP, Ruby, and Python. Our main site is thestar.com, but we also manage a few other sites, so I wanted to give you a quick overview of some of those sites. So MyStar is our personalization service, and it's really it's integrated with thestar.com, but it's a standalone Ruby on Rails application. So we use a lot of the standard caching approaches within that application. Wheels.ca is one of Canada's largest automotive verticals, so really focused on automotive content, as well as used and new car information finding. Toronto.com is quite an old site that is focused on what to do in Toronto. So it serves both the citizens of Toronto as well as tourists. So if you're ever in Toronto, Toronto.com will tell you what you can do around town. The Grid.to is an alternative news weekly, much like something like the Village Voice. So it's really focused on a younger demographic and overlaps a bit with the Toronto.com in terms of things to do, but also covers local news. So into caching. Why cache? And Nihar and Chris have covered this in some detail, but this is sort of the way I think about it. There's these 4 areas that we attempt to address by caching. So the first one clearly is performance. The closer you can serve content to the user, the faster their experience will be. So the goal really is, as much as possible, to push the serving of content out towards the edge, and whether that's in the edge, in the web tier, in the application tier, or in the database, but pushing it out. Scalability, and I'll show you a bit more about this, but again, the more you can push that content closer to the user, the more content you can serve and the more you can leverage the scale of the edge caching. Reliability, so what caching does give you is a level of redundancy. So essentially you're creating copies of your content at various tiers. If you have an issue with one of those tiers, the tier in front of it can continue to serve that content. So if you have any anomalies in your back end, in many cases your cache can help you or save you from an end user impacting event. And finally, cost. And the way I think about this is the further back into my infrastructure I have to respond to a request, the more it's going to cost me. So a database query is more costly than an app server query, which is more costly than a web proxy query, which is more costly than a CDN query. So the more we can get cache hits further forward, the less it's going to cost us overall. So a quick real-world example of how caching can help you. Some of you may recognize this guy. He's been in the news a little bit lately. This is the mayor of Toronto, Rob Ford. The Star has really been leading the charge in terms of reporting on his shenanigans. And in certain cases, we managed to get our hands on exclusive content. So this was about 2 weeks ago that this event happened. We published an exclusive video of him misbehaving. Okay, so clearly, as the guy responsible for the web infrastructure and development team, I was very concerned about the volume of traffic we would see and what would happen. So we also use New Relic, which is a great tool. Highly recommend it for profiling some of this stuff. This is a snapshot of that moment in time. It was about 12:15 on a Thursday afternoon. we were running at sort of our normal average request per minute from a browser perspective, about 2,500 requests per minute. And then within 15 minutes, we more than doubled our traffic. This is this is the view from the browser perspective. So you can see a massive influx of traffic. In this case, we don't have auto scaling on our app servers. We scale up manually. However, because of the various caching tiers we put in place, this is what it looked like from the server perspective. So our app servers continue to hum along at more or less the same rate they normally would have. And this is really the key to all of this discussion of caching, is to create that delta between what the browser is doing and what the server is seeing. Okay? So I'll take you through some of the approaches we take to creating that effect. So we're in keeping with the food theme, although my food isn't as interesting maybe as the cake and the burgers and fries, but I like to think of caching as an onion in the sense that it's multi-layered, and if you don't do it correctly, it will make you cry. Right? So let's dig into the onion. I think I need cake too. So another view of the onion, and very similar view of the various caching tiers, from the edge on the outside of the onion to the reverse proxy or web tier, to the app server tier, and to the database in the core. So the edge, the onion skin, and this is really the content delivery network part of things. Some examples of that are Akamai and CloudFront. In our case, we use CloudFront. You can think about CDNs from a pure static asset caching. That's the traditional way of thinking about a CDN. So my images, my JavaScripts, my CSS gets served that way. But interestingly, you can also do full site caching, and that's our approach with the star.com. Some important ideas to think about there are how you configure your origin servers and how you think about behaviors. And someone corrected that, it was spelled the Canadian way before. Anyways, so behaviors allow you to give you fine-grained control over how you serve different asset classes through your CDN. We use CloudFront across just about our entire network. All of our sites are using either full site caching or static asset caching. So this is a quick overview of the star.com's architecture, and you can see various caching tiers here. The key thing is that CloudFront is in front of our load balancer, and we have a single origin approach to this tier of caching. So in terms of our whole site delivery approach, here's some of our kind of philosophical and some of the things that we think about. We try to cache everything possible. So there isn't any asset class within the star.com that is not behind the content delivery network. In order to do that, we took some architectural approaches. Although CloudFront will cache based on cookies, we decided not to use any server-side cookies in order to maximize our caching capabilities. So when we do need to write a cookie, we try to do that on the client side in JavaScript. We only accept query strings when it's absolutely necessary. An example of that is our search page. So we'll cache each individual query string separately on our search page. So the screenshot you see here is of all of our behaviors. So we have 19 different rules, which allows us to specify different time to live and different parameters that we accept for different asset classes. So you'll see search, image classes. We can also control how we cache based on time. So if you look at 3/4 of the way down that list, you'll see things like 2009 star, 2008 star, 2007 star. We can set different rules, expiry rules on the caching of our content based on how old it is. So an article from 2007 can be cached longer than an article from 2010, let's say. A couple other points there. We use that single origin behind CloudFront, but we're scaling it across multiple availability zones for redundancy. And we're also working on spinning up an environment in US West, just for DR purposes, that will also leverage CloudFront. So moving down to the next layer of our onion, the reverse proxy, sometimes called a web accelerator tier. And this looks quite a lot like a CDN, but it lives within your infrastructure. Some examples, and we use all three of these, are Varnish, Nginx, and Apache. Varnish being more of a pure web accelerator product, and Nginx and Apache can be used for both as web servers as well as reverse proxies. So these all serve, I say static content in brackets because certainly they serve images, JavaScripts, and style sheets and the traditional static content, but also if you think about an HTML page that's generated by your app server, for a moment in time it becomes static. So based on the rules you set up in your reverse proxy, you're going to be taking that HTML page, maybe changing every minute, but that static copy that you have for that minute in your reverse proxy accelerates things in the sense that it reduces the load on your app server. And we use this strategy across a variety of things. I'm going to show you the examples of a couple of them. So MyStar is, as I said, it's a traditional Ruby on Rails app. There it is living, floating on top of the star.com. So what MyStar does is it provides the user with a personalized view of our content. So it's where they create their user profile, where they sign into the site, and it also allows them to customize content, things like their weather, their horoscopes. It allows them to follow writers and sports teams. And so pretty much every view within that application is on a user-by-user basis. So it's a different approach to how we do caching than on the star.com, where it's a semi-static site. So there's the sign-in view. Okay. So this is the MyStar architecture overall, and what we have here is a load balancer with reverse proxies across availability zones and app servers talking to a database, and there's caching at all these different tiers. So in this case, these reverse proxies are Nginx servers, and they're talking to the app server, caching the results, and they're able to serve those very quickly. In the case of our wheels.ca product, we're using Varnish for essentially the same thing. Varnish is an incredibly performant tool. You don't need a very large instance to serve literally millions of page views. The key there is that Varnish tries to keep things in memory. And it has interesting tools you can use to profile the cacheability of things. It's called things like Varnish Stat. Moving along, app-level caching. So there's various strategies here. This is really to accelerate how your app server works. The examples of this are Memcached and Redis. Elasticache now supports both of these products. Recently added Redis. So we use app-level caching really for two things. Chris mentioned session caching, and this is exactly what we do within MyStar. Within traditional Rails apps, you really have three options in terms of sessions. You can store your session in the cookie, you can store it in the database, or you can store it in something like Memcached. Memcached gives us a good trade-off between persistence and lower constraints and performance. When you use cookies, you're limited in terms of what you can store in the session, and clearly it's more volatile. The user can delete that cookie and the session goes away. On the other hand, if you use a database, you get an order of magnitude lower performance than with Memcached. So we decided to use Memcached for our sessions. Rails also gives you view caching, so essentially commonly served pages and page fragments are automatically stored in Memcached for performance purposes. Okay. So a quick view of that is really you have your cache. It's really we think of it as being in the database tier. We're using the Elasticache service, so it's very low maintenance for us. Okay, so getting to the core of the onion, we have database caching. And really, the goal here is to reduce the load on your database server itself. And Memcached is the way we do this. So we're able to cache frequent SQL queries, things that get queried over and over. In the case of MyStar, we have, let's say you follow a writer. Well, all of their articles will appear in a view. That's a given query. So Memcached allows us to query for those articles once, and based on a timeout, always serve that same content. Another example of that is wheels.ca, where we have this feature called the vehicle finder, which allows the user to build fairly complex queries. They don't know they're building queries. They know they're just interacting with the interface. but we have all makes and models of cars, geographic queries, and that sort of thing. So with Memcached, we can take that query that user's done, and then when a user comes back and tries to make that same query, it's reducing the cache, it's hitting the cache and reducing the load on the database. So here's what that architecture looks like. I showed you wheels.ca before, but that's really happening in the database too. So that's pretty much it for me. Thanks so much, and I guess I'll hand it back to Chris.
Thanks, Steven. So that's pretty much it for us up here today. On behalf of myself and Nihar and Steven, I want to thank you for coming to this session. On behalf of Amazon Web Services, I want to thank you again for coming to reInvent this year and sticking around to Friday. We'll be up here on the front answering questions for a little while before the next session. But thank you again for coming, and enjoy the rest of your stay here in Vegas.